So we're going to review function operations and function composition. And if you were with us yesterday and we were talking about how to evaluate functions, it's kind of the same thing, except now we're going to do a couple of extra pieces, almost like doubling the amount of work that we have to do. But it really isn't too bad. We just have to make sure that we stay calm, that we pay attention to our signs, and that we plug into the correct function, and that we do our order of operations well. Alright, so with function operations, you're going to see a notation that looks like this. F plus g of x. And what this means is that we're going to do f of x plus g of x. So even though the notation has it kind of combined like this, what it really means is that we can separate this to look at the two functions individually, and then we can add the results. And this is going to be true for all of our four main arithmetic operators. So f minus g of x means f of x minus g of x. If we have f and g right next to each other, well, that means that we're doing f of x times g of x. And finally, if we have f over g of x, that just means that we are dealing with the quotient f of x over g of x. However, we've got to make sure that we pay attention to this. There is a condition here that when we have the division of two functions like this, the denominator, that g of x function, cannot be the zero polynomial. So as long as we're not dividing by 0, everything's going to be okay. Alright, so we're going to make this as nice and simple as possible. It really isn't that bad. Again, it's all about paying attention and plugging into the right function. So if I say that f of x is equal to 7x minus 2 and g of x is equal to negative 3x plus 5. Okay, so we have these two functions, and I'm just going to ask some, well, fairly simple things. I'm going to ask you to evaluate. I want you to evaluate f plus g of 9. So f plus g of 9 means that you're going to take that input value of 9, you're going to plug it into both f and g, and once you're done doing that, do that separately. Once you're done, you're going to take those results and add them, because that's what this guy says. So the first thing you need to do when you see a problem like this is to rewrite it and to say that this is f of 9 plus g of 9. Do that and understand that you have two separate problems now that you're dealing with. Okay? So you know how we like to color code things. I'm going to use pink for f, and I'm going to use this fantastic blue color for g. Oh, good afternoon, Sarah. Hope you're doing well. Thanks for stopping by. So what I want us to do is I want us to take each of these guys and off to the side, evaluate them. So first things first, we have f of 9. So f of 9 is equal to 7. And again, we're using parentheses when we do the substitutions. So 7 parentheses, excuse me, parentheses 9 minus 2. And it's just a matter of doing our order of operations. So we get 63 minus 2, and we get 61. Now understand that 61 is not the final answer. It's what f evaluated at 9 equals. But now we need to go to the other side of this and figure out g of 9. So using my blue pen, g of 9 is equal to negative 3 use parentheses when you do that substitution. Plug in 9 and then plus 5. Make sure that you have everything written. You've got your negative 3, x has become 9, plus 5. Now we do the order of operations, so that's negative 27 plus 5, and these guys combine to give me negative 22. So now we go back to the main part of our problem. So the main part of the problem had f of 9 plus g of 9. And we found out that f of 9 is equal to 61, so I'm just going to plug that in right here. And g of 9 is equal to negative 22. So we go off to the side, we work out each of those guys, and now we bring them back in and we do the operation that's indicated, in this case, addition. So when I clean this up, that's just 61 minus 22, and 61 minus 22 is 39. And so that is the end result. And if you do what I'm doing here, it makes it really, really, really simple. If you try to do it all in a single line right here, as you were trying to do f of 9 and g of 9 all together instead of separately, it can be a really big mess. Now, it's not so bad because of the addition, but when you start doing other operations, it can get really messy. Now, if we take the same problem that we have here, I'm just going to add a little bit of an extra piece to it. So using the same f and g, if I had said do f minus g of 9, we already know what f of 9 and g of 9 are, but this now becomes f of 9 minus g of 9, right? And if we do the same thing that we did above, and we use those parentheses for the substitutions, because I want to make sure that I don't miss anything. It's very easy to get careless, and you write the wrong number, or you write the wrong sign. So f of 9, because we've already done this, is 61, and g of 9, we already said, is negative 22. So that didn't change from the first time that we did it. The only thing that's changed is that now I'm asking you to do subtraction. And by having the parentheses there for when we plug those function values in, it makes things a lot easier to read. So when we get to the next to the last step, we clean this up. That's 61. This now becomes a plus 22, and now we're not going to have any issues with our signs. 61 and 22 gives us 83. Just like that. Hey, Backlog. Good to have you here on the stream. And I'm glad you think this is a beautiful thing. I like to look at my work and think of it as a work of art. I try really hard to make things look nice and neat for my fantastic students that are out there lurking in the chat. You know what? I could do something else here if I said, just because I don't have to do a bunch of work over and over again, if I do fg of 9, this means that we're going to do f of 9 times g of 9. And again, using parentheses, like every good boy and girl will do, f of 9 is still 61. You don't need to re-evaluate that because we're still using the same function f, we're still using the same function g, and this is negative 22. Alright, so now we just have to multiply this. And let's see, we know the answer is going to be negative. We at least have that much. So that's going to be 122. So that's going to be 2. Man, I'm going to mess this up. I know it. So I'm just spitballing here, and I hope that's right. You know, we should probably check this, right? So it's going to give me 2. That's going to give me 12, 14. Yep, 13, 42. I'll take it. But you know what? I know some of you out there don't believe me. And I don't really like the way my negative sign is looking right here. Let's go to the calculator because I know you guys trust the calculator. Oh, pretend you didn't see that. And so I do 61 times negative 22, negative 1,342. Just like we rehearsed, right? All right, so seems fairly straightforward, I hope. Let's do some different functions, some different operations, and see if we can still process this well enough. All right. So if we are given f of x is equal to, here's where I'm going to throw you off, negative x squared minus 5x, and I'm going to tell you that g of x is equal to 6x plus 5. Okay, so you've got these two functions, and now I want you to evaluate what sounds good. Let's do g minus f of negative 8. So g minus f of negative 8. What does that mean for us? Do not be overwhelmed by this expression. Break it down into its smaller pieces. So this is g of negative 8 minus f of negative 8. Yes, Nydia. Oh, no. No, this is not going to be multiplication because we have the subtraction here, right? And so when we break this down, we're going to evaluate those two functions individually, and then we're going to subtract those results. And when it comes to subtraction, it has to be in this order. I said g minus f. So you're going to have the evaluation from g, and then you're going to subtract what you get from f. If I didn't have that subtraction, they were right next to each other, then that would indicate multiplication. All right, so off to the side, we're going to break these guys down. Now, you know me. F is going to be pink. G is going to be blue. And so the first thing I need to do here is find g of negative 8. All right. Now, if you don't like going up to the side here and you would just rather have like your own piece of paper to do all the scratch work on, go for it. I like to see the work from you guys out here on the side. That way, if you make a mistake with that, maybe you just miss a sign for one small part, I'm not going to take off all the points for the problem. I want to be able to see your work. That way we can, if there are mistakes, we can correct those and we can learn from those and be better the next time. So 6 times negative 8 is negative 48 plus 5, and we get negative 43. So that's only part of it. Now we need to go and find f of negative 8. All right, remember, when we plug in, use parentheses. So when it comes to having multiple pieces like this, and when you've got the square and the negatives, make sure that you use your parentheses very well, like this. So the parentheses are in place. We just replace all of the x's with a set of parentheses, and now we're plugging in negative 8. Now be careful when it comes to the order of operations. Here, this negative outside and the negative on the 8, they don't get to see each other. The square has to happen first. So this is negative. This becomes positive 64. And then minus 5 times negative 8. We keep working this. This becomes negative 64. This becomes plus 40. And these guys combine to give me a negative 24. And so now what we're going to do is we're going to take those numbers and plug them back in up here. And as we were doing on the previous examples, we use parentheses. G of negative 8, so this guy was blue, this becomes negative 43. And then f of negative 8, f of negative 8 is negative 24. So from here, clean up those parentheses, so that's still negative 43, but now minus a negative 24 becomes plus 24. And we combine these integers, and we come up with a negative 19. Okay? What do you guys think? Do you have any questions about what we did for that one? Or does it all seem to be mostly okay. So let's keep working with the same two functions, f and g at the top of the page. And let me ask you to do this. If I ask you to evaluate what do I want to say? Let's do g over f of negative 5. So having g over f of negative 5 means that I need to evaluate g of negative 5. I need to evaluate f of negative 5. And then once I have those two evaluations, I'm going to do division. In that order, g divided by f. All right. So I wasn't using negative 8 as I did in the last example, so we're going to have to go back and evaluate these guys brand new. All right, so let's see, g of negative 5. So g of x was 6x plus 5, and if you happen to forget what the function was, maybe just above it, you kind of write that function again. You say, okay, g of x equals 6x plus 5, okay? Now remember, that's g of x. When we say g of negative 5, the x is no longer there, and the x has been replaced with the input value of negative 5, like this. Working this out, we get negative 30 plus 5, which gives me negative 25. And then we move on to the denominator. And let me just really quickly write that function. F of x was equal to negative x squared minus 5x. So we've got that there as a formula, and we need to evaluate f of negative 5. Negative, parentheses, squared, minus 5, parentheses. Don't forget the little things, because that's what keeps you from getting in trouble. Plug in negative 5, and now let's see what we get. So this is negative. This becomes positive 25 minus 5 times negative 5. So that's negative 25 plus 25, which now becomes 0. Right? Everything was going so well until then. Okay? So, I mean, not that 0 is a bad number, but let's see what happens when we plug these guys in. Here's my fraction. In the numerator, I guess I don't really need the parentheses here, we get negative 25. In the denominator, it's parentheses, and f of negative 5 is 0. So we have negative 25 divided by 0, and you guys know what the answer is, right? What happens when you divide by 0? I know someone out there can make me proud. Remember, I don't even know if I want, do I have the energy to sing? When 0 is under the line, the expression is... No one? No takers? All right. The expression is undefined. There you go. Right? So we tried doing this evaluation, but we ended up with something that was undefined. Now, if this had been switched, okay, so if instead we had f over g of negative 5, so that would mean f of negative 5 divided by g of negative 5. In this case, we would have 0 in the numerator, we'd have negative 25 in the denominator, but this would just become 0, right? So when the denominator is 0, the expression is undefined. But if it's just the numerator that's 0, 0 over any non-zero denominator is going to become 0. So there you go. I mean, that's doing function operations. Now let me do a little extra thing. So some of you may have seen this in the homework. I don't think this was in everybody's homework, but let's talk about doing function operations from a picture. Problems with fractions. You know what? Fractions never go away. Take your time. Just gotta, start on the shallow end before you dive in deep, right? So let's look at this. Now I'm going to call this lighter guy right here. Let's call this one f of x, and let's call the line. We're going to call that g of x. Okay. So from here, I'm going to ask you questions. I'm going to ask you to find the following. I want you to find f plus g of 1. So without even looking at the picture, you need to know that when I write f plus g of 1, that this means f of 1 plus g of 1. And in order for you to evaluate the function, you don't need to know what the actual function is. You don't need to know that formula. You just need to be able to look at the picture and identify the y-coordinate. Because remember, your function value is the y-coordinate. And it's in this one, it's going to be the y-coordinate when x is 1. So if we look over here, so if we look over here, when x is 1, you're right here. So f of 1 is going to be matching up right here. So when x is 1, you see that for f of 1 is going to give you an output value of 1. So this is equal to 1. And then plus, what's g of 1? Well, g is this line right here. And when x is 1, you see that you're down here. And down here, you're at the ordered pair, positive 1, negative 2. So when I ask you what is g of 1, I'm asking for the y-coordinate when x is 1. Okay, so when x is 1, we see that the y value is negative 2. And so now we just put these guys together. 1 and minus 2 gives me negative 1 for that evaluation. And remember, we're just getting the pictures, or we're just getting the output values by looking at the graph. So if I ask you for, let's say, f minus g of 0. Alright, so f minus g of 0 means find f of 0, find g of 0, and then subtract those values. So we're going to look at the picture here, and we're going to find f of 0 and g of 0. So that's going to be when x is equal to 0. So for our function f, this parabola, when x is 0, you are up here at this point, so that gives us an output value of 4. So f of 0 is 4. Minus, what's g of 0? Well, g is the line, and when x is 0, you have this ordered pair right here. So you get 0, and the output, the function value, is negative 1. And so from here, we just clean this up. That's 4 plus 1, and we get 5. And again, we're just taking what we see in the picture, taking those y-coordinates to evaluate the functions, and then we either add, subtract, multiply, or divide. All right, let's do one more. Let's do f g of 4. All right, so with f and g right next to each other, that means that we're doing f of 4 times g of 4. All right, so let's look at the picture. We want to find f of 4. So we're going to come over here where x is 4, and we're up here 1, 2, 3. Looks to be right here. We have the ordered pair, that when x is 4, y is 4. And while we're here, let's look at the g function. So when x is 4, you are at this ordered pair. So 4, comma, negative 5. So you identify those points, and you take the y values because that's the function value for these guys. So f of 4 we found to be over here is 4, and g of 4, you plug in 4, you get out negative 5. And then you just do the multiplication because that's what it says to do. And we get an answer of negative 20. So that's how we do these function operations when we were just given pictures. You didn't need to know what the actual function was for this or for that parabola. You didn't need to know that. You could find it out. But at this point, it's not really worth it. All right, so that's function operations. Let's now talk about function composition. I know you're all excited about this. There are a lot of weird analogies that I have in my head for function composition. There we go. All right, so function composition. When we were doing function operations, we evaluated two functions separately, and then we came up with a result, whether we added it, subtracted, multiplied, or divided. Okay, that's what we were doing. Function composition works a little bit differently. And what function composition does is that you don't go individually. You have to do this guy first, and then you plug it into something else. So this is more of an assembly line type situation. Okay, if you guys remember the scenarios that we did in class, I did it with like the markers, right? So function operations would be me giving you a black pen and you a black pen, and you do whatever you do with this, and you combine the results, right? But function composition says I'm going to give one person a black pen, and they do what they do according to the function that's in them, and then they give the result to somebody else. So the other person doesn't get the original product. They just get whatever's left over. Okay? So here's the notation that we see for function composition. Okay? We see this little open circle. This is not multiplication. And this is why whenever we do multiplication with functions, you don't see me do that little raised dot that we typically use for multiplication. I just put those guys right next to each other because that juxtaposition indicates a product. So I'm going to use this symbol for composition. Don't get that confused with multiplication. And what this means is that you're going to do f of g of x. And that's it. That's what it means. Another way of looking at this is that function composition is like the inception of mathematics, right? You have a function inside of a function, Or you can think about it as a turducken, right? A turducken, what is that? As a chicken stuffed inside of a duck, stuffed inside of a turkey. I hear it's a real thing. I've never seen one, but I know that's a real thing. And that's what you're doing here. You're taking x, and you're going to stuff it inside G. You're going to take that result and stuff it inside F. Okay? So order is going to be very important here. So if I say that f of x is equal to 4x plus 9, and g of x is equal to 7x minus 2. I want you now to evaluate f of g of 2. Let's find f of g of 2. Now, you know me, I'm going to go back to color coordinating things. So pink is going to be for f, blue is going to be for g. Let's make sure we understand what this notation means. F of g of 2 means f of what? Well, f of g of 2. So you can't even do anything with f yet. You have to take g off to the side and evaluate that guy at 2. So you can imagine for this problem right here, that here is your assembly line. And you've got 2 workers, right? You have f of x right here, and you have g of x right here. And so this assembly line is going in this direction. Well, what happens? Here is x. X is coming along this assembly line, and he's going to go into g first, and he's going to get passed along here, and then that result's going to go into f. That's function composition. In this case, we're plugging in 2. So off to the side, we're going to find out what g of 2 is. I mean, this is nothing more than what we've been doing yesterday and today. You replace the x with 2, and you do the math. So 7 times 2 is 14, minus 2 equals 12. So we now have, instead of f of g of 2, this is f of 12. All right, so it's f of 12, and off to the side, let's figure out what f of 12 is. So f of 12 is 4 times 12 plus 9. All right, so working this out, 4 times 12 is 48 plus 9, and this gives me a grand total of 57. So over here, f of 12 is 57, and now we're done. Now this was doing f of g of 2. What if I swap the order around? What if we do g of f of 2? Will it be the same? Does the order really matter? Let's find out. So g of f of 2, excuse me, means g of f of 2. So here in this problem, g is the one who's playing the waiting game, right? 2 gets plugged into f first, so f does whatever he does as a function, and then once f is done with it, he passes it along to g. Okay, so off to the side, we're going to figure out f of 2. So that's 4 times 2 plus 9, 8 plus 9, and that gives me 17. Let's make sure I'm doing this right, because I feel like I'm not thinking clearly. Let's see. I did 2 into f. I followed the function that I have up here, so 4 times 2 is 8 plus 9, 17. Okay. Sometimes I have to double check myself, because there was this one time, I'm not proud to admit it, where I said 4 times 2 is 6. It caused some problems. But I learned my lesson, and I try to do a better job of checking my work. Although Kevin was here the other day, whenever I don't even know what I was doing. I had some wrong numbers, pulled wrong numbers out of my head and it was bad. And this is why we have correction tape. Alright, so now we have to do g of 17. Alright. What was g? G was 7x minus 2, so 7 times x, which is 17 minus 2. So 7 times 17, that's 70, 49, 119. Minus 2. And all together we get 117. Okay? What do you guys think? Nice and easy, right? So that's 117 at the end. So you see that the order definitely makes a difference. Okay? When I did f of g of 2, I got 57, but then g of f of 2, I got 117. Not even close to the same number. So order does make a difference. And you know this if you've ever worked on an assembly line, right? If all you're doing is one particular thing to whatever's coming down the assembly line, and the person after you does something different, if you guys swap the order in which you do things, you're going to get a totally different result. All right. So let's do a couple more, because why not? And what else are you going to do? It's Thursday. I mean, Price is Right is already over. Wasn't that over at 11? I honestly don't know. That is a good question. So the main part of, I guess, the way I'm seeing doing function composition is getting people ready for whatever math they're going to be taking later on. Understanding that you can plug one function into another one. For example, let's look at it this way. If I say f of x is equal to the square root of x, and g of x is equal to 3x plus 5. What we're going to do now is we're going to look at some composition where I'm not actually plugging in numbers, but I'm going to take one function and plug it into something else, because sometimes that's how functions are composed. And so when you go on to take higher order or higher level math classes like calculus, you need to be able to break it down to see what the big function is and what the little function is that's been plugged inside of it. In terms of working with magnetic fields or economics, I don't really know about those applications, so hard to really answer that. But in terms of like how do functions work and understanding certain limitations, let's look at this example right here. So if I want you to find, for example, f of g of x. Well, I'm not asking you to plug in a number. I'm asking you to just do it in its raw form. This means to do f of g of x, right? So this means I need to evaluate. Here's the thing, I can't really evaluate g of x because g of x is that guy. What this means, though, is that we're to plug in the entire function 3x plus 5 into f. That's what we're supposed to be doing. Right, we did some of these examples, I think maybe it was yesterday, plugging a variable expression into another variable expression. So when I do that here, f was the square root of x. So whatever you plug into f, you are just plugging into the square root of this guy. So this is the square root of 3x plus 5. So you have this composition. You have taken two different functions and you put one inside of the other one. Now, let's talk about domain and range on this. So, do this. Let's talk about the domain of f of x, which is equal to the square root of x. So, when we talked about domain and range, well, we talked about domain a long time ago. We said that for most of the functions that we're going to see, there are only going to be two things, at least right now, until after our second test, only two things that are going to limit our domain. Because for the most part, your domain is going to be all real numbers. The two things that can restrict our domain right now are square roots and rational expressions, fractions. So I have a square root here. And with the square root, you remember that the parent function is not, it does not have a domain of all real numbers. The domain is just from 0 to infinity. anytime you want to try to find the domain of a radical function, your domain is going to be taking that radicand, x, and solving the inequality where it's greater than or equal to 0. So that's already solved for x, which means our domain is going to be bracket 0 to infinity. And what that means is that if I were to take that square root function and plug it into something else, he is going to be carrying along this limitation on the domain. It doesn't matter what ends up getting done to the square root function later on. If you plug it into something else, his original domain and the restrictions must carry along with that. Now compare this to the domain of g of x, which is equal to 3x plus 5. Okay? So do we have any radicals? No. Do we have any fractions where x is in the denominator? No. So here, our domain should be, and is, all real numbers. There are no restrictions on that guy. Okay? So those are the two individual domains for our functions. Now let's look at what happens when we do the composition. When I do f of g of x, I plugged in something that didn't have any restrictions. But the square root function does have restrictions. So if I want to find the domain for this, my domain means I'm going to have to take the expression that's inside here, and we have to make sure that this expression is non-negative. It has to stay greater than or equal to 0. And as we solve this inequality, you go through the steps, you subtract 5, and you divide by 3. This ends up being our restriction on x, which ends up being our domain. So your domain for this guy would be from negative 5/3 to infinity. So you brought in somebody who didn't have any restrictions on the domain into a function, the square root, that did have restrictions, so they have to play nicely with each other. Now I want you to watch what happens whenever I swap these guys around and I do the composition in the other order. And let's see what happens to the domain that way. When I do g of f of x, all right, so that means g of f of x like this. So that means in my function g, I'm going to be plugging in f. And f, as we saw above, is just the square root of x. And what does g say to do? G says that you're going to take, when I say g, oh, come on now, what are you doing here? All right. So g says you're going to do 3 times your input value plus 5. So I'm plugging in the square root of x. And there's really not much to do here, so you just write 3 square roots of x plus 5. But let's talk about the domain here. This square root of x has a restricted domain from 0 to infinity. When you plug it into this guy, he is still carrying along that restricted domain. Now, this is the only guy that's going to restrict anything, so my domain is going to be that of the original function f, and that's going to be from 0 to infinity. So two different compositions gave us two totally different functions, which also had two different domains. Now, going back to what we were just talking about with function operations, if instead I wrote this and I say f plus g of x, and I want to look at it in its raw form, that is f of x plus g of x, and now we're just going to plug those guys in because we're not evaluating anything, we're just going to plop those functions as they are. So f of x is the square root of x, and g of x is 3x plus 5. To find the domain, whenever you are adding functions, the domain of the addition is going to be the intersection of their individual domains. So for this guy right here, his domain was from 0 to infinity. And this guy had a domain that was all real numbers. Now to find the domain of the whole thing, you've got to look at their intersection. So if you can see it, great. If you want to graph it out, you can do that too. Because as we showed a long time ago with doing intersections, just kind of graph them on top of each other. So from 0 to infinity, 0 to infinity looks like this. And this is all real numbers, so that's all the way left and all the way right, like this. And we're trying to find out, where do these guys intersect? These guys intersect right here, which is going to correspond to this part of the number line. So their intersection is going to be from 0 to infinity. This guy has limitations that cannot be lifted. Okay, so no matter what you do, you have to deal with those limitations. Even if we had something like this. So still sticking with the square root function, because we know what his domain is. Where are you? The reason we can't use the union, and if we had done the union on this last example, the union of these two guys would have been all real numbers. And if we try to union those guys together, then you're saying that I can plug in any number that I want to, all real numbers, right? But we can't, because if we plug a negative in here, we're going to end up with something that's imaginary, right? So think about it this way. Think about if you know people, you're trying to bring everybody over for a dinner party, and you're trying to cook for them. And you know that one of your friends, has to eat gluten-free. And you have another friend who doesn't eat meat. So already you have restrictions. So if you're trying to make a meal for them, you have to make sure that meal is going to be something that's going to be the intersection of what they can eat, right? So the intersection is going to be something that is gluten-free and does not contain meat, okay? That's going to be the domain of what you can cook. And that's what we have to deal with whenever we have function operations going on here. Because if one guy is already limited, that's going to limit everybody else, right? It's just like if you are going to hang out with your friends and you're 20 years old and all your friends say, hey, let's go to a bar. Well, since your age is less than 21, you're not going to be able to go to the bar. So instead of them going to the bar, they're going to do something that fits with everybody's domain, right? Which is going to be everything that is legal, right? Everything that's legal for someone who's 20 years old and older, right? So, hope that makes sense. If I say that f of x is equal to the square root of x and g of x is equal to x squared plus 3. Let's see what happens here. I know this is maybe not quite what you were expecting, but if I do one composition versus another one, let's see the difference here. So f of g of x means f of g of x. And so I'm going to plug g of x, which is x squared plus 3, into f. So I end up with the square root of x squared plus 3. All right? So that's, yeah, there's going to be some weird stuff here. And then in a moment, we're going to make a slight connection to calculus, if you guys want to see some really fun stuff. It might be a little bit much, but calculus is super fun. if I look at this and I want to find the domain, okay, notice that the domain for this guy right here, let me go and write this above. So his domain is going to be all real numbers. There are no radicals, there are no fractions for this guy, so you can plug in any number into G and it's going to be fine. It's going to give you a real number. Over here though, as we saw on the last page, his domain is from 0 to infinity. Okay? So inside here, he didn't really have any restrictions. So his domain is going to be all real numbers. But now it's inside of a square root. So here's what we have to do. We have to take the expression inside here, right? And so to find the domain, we have to solve the inequality where x squared plus 3 is greater than or equal to 0. And what you're going to find out with this, because we did solve quadratic inequalities earlier this semester, this guy right here is going to be actually all real numbers. X squared plus 3 is always greater than or equal to 0. If you think about what this looks like as a graph, okay, x squared plus 3 is going to be a parabola whose vertex is right here at 0, 3, and he's going up like that. When we were doing these quadratic inequalities before, we were saying find those critical values where it hits and goes below the x-axis, right? Because that way you can divide it into where he's greater than 0 and where he's below 0, right? That bottom part of the parabola. Well, notice that this guy, his entire graph is above the x-axis. That means no matter what value you plug into this, it's always going to be positive, okay? Or in this case, non-negative. So the domain for f of g of x is going to be all real numbers, which I think is kind of cool. Doesn't matter what number you plug into this, you're always going to get a positive result, and you can take the square root of a positive. But let's flip this around. If I do g of f of x, right? So now that means g of f of x. All right, so I'm now plugging in the square root of x into g. Now this is where things get a little bit tricky. That means I'm plugging in, I'm going to use some extra color here. I'm plugging in the square root of x into the function g. Now you guys will say, oh, when you square the square root, it's like those guys cancel, it's like they simplify away, and you're just left with x. And then plus 3. Now, if you had not seen anything else up to this point, and you just had this expression right here, and we were to talk about what's the domain, we would say the domain is all real numbers. But we can't say that. And the reason we can't say that the domain here is all real numbers is because you are restricted by the square root of x that was being plugged into that. So this guy has a domain that still has to be from 0 to infinity. Okay? And you might say, well, I don't see why I can't plug a negative in here, because really what's going on is that you would have to take care of the square root first before the square, right? And so we have to make sure that we are sticking with real numbers all the way. It's kind of weird, but that's just kind of the way things go on this. Now, let me show you one of the ways that we end up dealing with these composition of functions. So suppose I have a function that is the composition that we had above, which was the square root of x squared plus 3. Now, one of the things that we do in calculus is we do this fun little thing called the derivative, okay? And what it is us taking a variable expression, it's taking a function, and coming up, just in simplest terms, it's coming up with a formula for the slope. Now, in the past, when you have slope, you're probably thinking about straight lines, right? And with a straight line, whatever slope you have is going to be the same throughout. But we have seen that not every function that we come across is linear. We have things like parabolas. We have the square root shape. We have absolute values, all kinds of weird shapes. And if we have something like a parabola, this guy's decreasing, he gets flatter and flatter, then he starts to increase. So his slope is changing all throughout. But the thing is, we can come up with a formula that tells us what the slope is, and that's called the derivative. Now, for something like this, we need to be able to see this as two different functions. We need to be able to see this as a square root, and then inside of this, we see this as something that's quadratic. You have to see it as two different pieces, but as a composition. And if you were to do the derivative, right, it's all about understanding how things are nested. And you know what, I'm actually going to rewrite this, just because for the purposes of a derivative. Man, I haven't done these in a long time. Look at it like this. So with the derivative, you would take the power, bring it out to the front like this, and you would keep whatever is inside this exactly the same. You take 1 off of the power, so that becomes a negative 1/2. But then here's where function composition comes into play. It's part of something called the chain rule. What you would do after this is that you would multiply times, and you take what's on the inside of this, and you're going to do his derivative. And we use that little apostrophe there to note derivative. And then we go to the next phase. So you did the derivative of the main part of the function, which was the square root, and now you do times the derivative of what was on the inside. And interestingly enough, the derivative of x squared is 2x, and the derivative of 3 is 0. And think about this. When I say derivative, I know it sounds like a fancy word, and you're probably tuning me out, but the derivative is the slope. And if you were to look at 3, think about what 3 looks like when you graph it. 3 is just a horizontal line. And what's the slope of a horizontal line? 0, which is why I don't have anything written there. X squared, his slope is going to be 2x, which means the further you go on that parabola, if you go to x equals 2, 3, 4, 5, and so on, it's getting steeper and steeper, and by that formula, right? If you plug in negative numbers, you're on this side, so you have a negative slope, then you become positive slope. Now if I clean this up, so this is really here's the thing about calculus. I just want you guys to understand. The steps that I'm taking, that's calculus, but you spend more of your time just cleaning things up and simplifying and really just doing algebra skills. So x is going to be here. Now I've got a fraction, and the reason I have a fraction is because of this negative power. You guys remember negative powers? We've talked about those. We talked about those in 0310. Talked about those in college algebra already. And a negative fraction just means that you go down, you flip it on the other side of the fraction bar. So this is what the derivative looks like. Again, we couldn't do any of this without function composition. All right. Well, that was a fun little diversion. I like derivatives. So much fun. Also know this. Sometimes you might see examples show up in the homework. I mean, I was assuming that you guys had already finished some of this homework before spring break. Let's do this. Let's say f of x is equal to x squared minus 4 and g of x equals negative 3x plus 1. And I want you to evaluate f of f of negative 6. So f of negative 6. Well, let's see. We already know what this means because we've talked about function composition. That means f of, and we have to evaluate f of negative 6. So this is kind of weird. This says that negative 6 is going to get plugged into f. And then we're going to take that result and plug it back into f. So g is not even being used right now. So off to the side, f of negative 6, just work this out. Negative 6 squared minus 4. So that's 36 minus 4, which equals 32. Right? And so now we come back over here, and we get to evaluate f of 32. So negative 6 went into f, and we got 32. Now we're going to put 32 back into f. All right, so let's see. f of 32 equals 32 squared minus 4. And we just work this out. Of course, you know what 32 squared is because it's one of my favorite numbers. 32 squared is 1024. I feel like I might have seen that somewhere before. And then minus 4. So altogether, this is 1020. So if I remember correctly, there's a problem that's very similar to this in your homework in my math lab. Yep. So it gives you like that g of x. It's just there trying to throw you off. And let's just do one more. All right. And let's use the g this time. I felt bad for him. So let's do f of g of 4. All right, so f of g of 4 means f of g of 4. So then off to the side, we're going to work out g of 4. So negative 3 times 4 plus 1. Remember, using the g that's at the top. That's negative 12 plus 1, which equals negative 11. All right, so now we're going to do f of negative 11, right? And as we do, off to the side, we're going to find f of negative 11. And so that means I'm going to replace the x with my parentheses, and I'm going to plug the negative 11 inside that. And so now when I square the negative 11, I get 121 minus 4, and we get 117. So again, the key thing here is to understand that the 4 gets plugged into g first. So you don't plug it into both of them, you do it one at a time. 4 goes into g, we get negative 11. Then that value goes into f, and we get 117. I need you to be careful, because it's very easy to get stuck doing a particular kind of problem, and then when they change it on you, you're not paying attention. So if I do this, if I write fg of 4, right? So what does fg of 4 mean? This is where it means multiplication, because this is where we have f of 4 times g of 4. When the f and the g are right next to each other, that means multiplication. All right. So we need to figure out f of 4. That's 4 squared minus 4. I mean, this is stuff we've been doing most of our lives, right? Follow the order of operations. 16 minus 4 is 12. So f of 4 gives me 12. Now we could do g of 4, do that off to the side, but you know what? We don't have to do g of 4 up to the side because we already did g of 4 up here. It's the same g, right? So instead of us recreating the wheel, this just becomes negative 11. And we multiply these guys to finish the problem. And we get negative 132. Okay. So in this case, we had two different functions, and we needed to evaluate each of them and then bring those results back together through multiplication, because that's what it was saying right here as f times g of 4. All right, so that's function operations and function composition. Make sure that you pay attention to your signs. Make sure that you are plugging things into your functions correctly. Now, tomorrow, you don't want to miss tomorrow, because tomorrow we're going to be graphing non-linear functions, dealing with the parent functions that we talked about before spring break. So that means we're going to be talking about your squaring function, your parabola. We're going to be talking about your absolute value, your v-shape. We're also going to have that little half sideways parabola, which is a squaring function. We have that snaky guy, which is your cube root function. And then you have cactus, right? The cactus one is the guy that is the cubing function. So we're going to look at those basic shapes. We're going to look at how we can shift things up, down, left, and right, maybe do some reflections, do some stretches, some compressions, and yeah. So make sure that tomorrow you come prepared with your graph paper, and I will do the same. So I will see you guys then.